Somewhere beneath the geysers, the bison herds, and the boardwalks packed with tourists snapping photos, something has been stirring that most visitors will never see with their own eyes. Yellowstone National Park sits directly on top of one of the largest volcanic systems on the planet, a place where the ground itself behaves less like solid earth and more like the skin of something still breathing. And in the summer of 2026, that system did something new. Not a super eruption. Not the disaster the internet loves to imagine. But a real, measured, scientifically confirmed change in the ground, one that instantly caught the attention of researchers who have spent their entire careers watching this place for exactly this kind of surprise. So what actually happened beneath Yellowstone? Why did it matter so much to scientists even though the public alert level never moved? And what does it really tell us about the risks hiding under America's oldest national park? To understand any of that, we have to go back to where this story truly begins, long before anyone in 2026 was paying attention. Yellowstone did not appear out of nowhere. Its origins stretch back roughly 16 to 17 million years, to a plume of abnormally hot material rising from deep within the mantle. That hotspot barely moved at all. Instead, the North American continent slowly drifted over it, like a sheet of ice being dragged across a candle flame. As the plate crept southwest, the hotspot burned a long trail across what is now southern Idaho, leaving behind a chain of ancient calderas that eventually became the Snake River Plain. Roughly 2 million years ago, that hotspot finally settled beneath the corner of Wyoming we now call Yellowstone, and the volcano as we know it was born. What followed were 3 colossal eruptions, the largest of which sent ash across much of the continent, an event so immense that geologists still study its fallout in sediment layers thousands of miles away. The most recent of the 3, the Lava Creek eruption, carved out the massive caldera that tourists now drive across every summer without realizing what lies beneath their tires. Since that last super eruption more than 600,000 years ago, Yellowstone has never gone fully silent. Dozens of smaller lava flows followed over the following hundreds of thousands of years, the last occurring roughly 70,000 years back. And even without any lava reaching the surface, the volcano has stayed remarkably active in quieter ways. Every single year, somewhere between 1,000 and 3,000 small earthquakes rattle the region, most too tiny for anyone to notice without sensitive instruments. Occasionally these arrive in swarms, dozens or even hundreds of tremors clustering together in a matter of days, and while that might sound alarming, scientists say these swarms are usually just fluid moving through cracks deep underground rather than any sign that magma is rising toward the surface. The ground itself rises and falls over time too, sometimes by several inches across an area spanning hundreds of square miles, as pressure from magma, gas, and heated water shifts beneath the crust. It is, in a strange way, a landscape with something like a heartbeat, one that scientists have learned to read closely because a change in rhythm can mean something worth investigating. All of that restless energy escaping from below powers one of the most extraordinary collections of natural features anywhere on Earth. Yellowstone is home to roughly 10,000 hydrothermal features, hot springs, mud pots, fumaroles, and steam vents scattered across the park, along with more than half of all the active geysers found anywhere on the planet. Every one of them depends on a hidden underground plumbing system, a maze of cracks and mineral-lined channels carrying superheated water toward the surface. Researchers understand the broad outline of how this system works, but the fine details remain surprisingly hard to pin down. Pressure can shift in one corner of a geyser basin and instantly change behavior somewhere else nearby, sometimes reviving dormant features and sometimes shutting down ones that have run reliably for generations. Steamboat Geyser, the tallest active geyser on the planet, illustrates this unpredictability perfectly. For decades it erupted only rarely, sometimes staying dormant for years at a stretch, and then, starting in 2018, it suddenly began erupting dozens of times annually with no fully agreed-upon explanation for the shift. All of this heat has to come from somewhere, and the scale of it is genuinely hard to picture. Yellowstone continuously radiates an estimated 4 to 6 gigawatts of thermal energy into the environment, comparable to the output of several large power stations running non-stop, all of it simply escaping into the Wyoming sky as steam and warm water. Most of that heat dissipates harmlessly. It always has. But it is precisely because so much energy is constantly moving through such a fragile, shallow plumbing system that Yellowstone's most immediate hazard has very little to do with a dramatic volcanic eruption at all. That hazard is the hydrothermal explosion, and it became impossible to ignore on July 23, 2024, when a sudden blast tore through Biscuit Basin, a popular thermal area just northwest of Old Faithful. Around 10 in the morning, without any detected warning signs, Black Diamond Pool erupted violently, throwing boiling water, mud, and rock hundreds of feet into the air. Video captured by stunned visitors showed people sprinting away as a dark plume of steam and debris rained down, destroying a section of the nearby boardwalk. Remarkably, no one was hurt. Investigators from the United States Geological Survey later confirmed the explosion had nothing to do with rising magma. It was driven entirely by water flashing suddenly into steam in the shallow ground beneath the pool, a mechanism completely different from a true eruption, but no less dramatic to witness in person. Biscuit Basin was closed for the remainder of that season, and in the aftermath, scientists installed a wave of new equipment around the area: seismometers, infrasound microphones, temperature sensors, and cameras, hoping to better understand a hazard that had clearly been underestimated for years. Nobody expected that equipment to be tested again quite so soon. Early on the morning of June 13, 2026, just after 5 in the morning local time, that same monitoring network picked up a burst of seismic energy paired with a low-frequency infrasound signal coming from the direction of Black Diamond Pool. At first, the natural assumption was that the same pool had exploded again. But when researchers checked the temperature readings, the numbers did not fit that story. If Black Diamond Pool itself had blown, its sensors should have recorded a sharp spike followed by a rapid plunge. Instead, they showed only a small blip. The source had to be somewhere else. A newly installed camera solved the mystery almost immediately, capturing a dark plume of steam erupting from the ground just north of the pool at the exact moment the instruments recorded the disturbance. When park geologists reached the site the next day, they found the landscape had genuinely changed overnight. 3 separate groups of vents had opened where solid ground had stood only hours earlier. The largest crack stretched more than 60 feet across the basin, in places widening to nearly 5 feet, and it was filled with water sitting right at the boiling point for that elevation. Rocks thrown out during the blast littered the area, though none had traveled particularly far, a sign that this explosion, while real and significant, released far less energy than the one in 2024. Gray, sediment-heavy water poured from the new vents downhill into the Firehole River, turning the water milky for miles downstream, visible even from the main park road. What happened over the following days is where this story becomes genuinely fascinating for scientists. Rather than settling down, the ground kept transforming. Sometime between the evening of June 14th and the morning of June 16th, a patch of earth that geologists had personally walked across just 2 days before collapsed inward and filled with vigorously boiling, gray water, forming an entirely new pool roughly 20 feet across. There was no debris field around it, which told researchers it had not formed through another explosion but through a quiet collapse into the hollow hydrothermal system underneath. Then, only days after that, the new pool began spouting on its own, sending water shooting 6 to 9 meters into the air in repeated bursts. Within the span of about a week, scientists had watched a section of Yellowstone go from solid ground, to an explosive vent, to a collapsed crater, to an actively spouting pool, a complete life cycle of hydrothermal activity condensed into days instead of decades. What made this event historic was not really its size. It was its timing and its location. The new monitoring station installed after the 2024 explosion sat only about 100 meters from where the June 2026 event occurred, making it the closest a hydrothermal explosion has ever unfolded to dedicated scientific instruments in Yellowstone's recorded history. For the first time, researchers had synchronized seismic data, infrasound recordings, temperature readings, and high-resolution video all capturing the same event from before it happened to well after it ended. Every previous explosion in Yellowstone's history had to be reconstructed afterward from debris fields and damaged boardwalks. This time, scientists effectively had a front-row seat, and that dataset is now at the center of one of the most important open questions in volcanic hazard research. Can these explosions actually be predicted before they happen? It helps to understand what a hydrothermal explosion actually is, because it is very different from what most people picture when they hear the word volcano. A true eruption is driven by molten rock forcing its way upward through the crust. A hydrothermal explosion is driven by water. Groundwater seeps deep underground across Yellowstone's basins, where heat from the surrounding volcanic system warms it far above normal boiling temperatures, kept liquid only because of the immense pressure trapping it in place. Over thousands of years, that same water dissolves silica out of the surrounding rock, and the silica slowly hardens into mineral deposits that can seal off sections of the underground plumbing like a lid on a pressure cooker. Heat keeps building beneath that seal. Eventually, something gives, sometimes a small earthquake, sometimes shifting groundwater, sometimes nothing anyone can identify at all, and the trapped water flashes instantly into steam, expanding hundreds of times in volume in a fraction of a second and blasting everything above it into the air, or causing the ground to simply give way. This is exactly why the United States Geological Survey has repeatedly pointed to hydrothermal explosions, not a supereruption, as Yellowstone's greatest immediate hazard to the people walking through it every day. The scale of that hazard becomes clearer when you look at Yellowstone Lake, where the shoreline near Mary Bay holds the largest confirmed hydrothermal explosion crater on the planet, stretching roughly 1.5 miles across. It formed around 13,800 years ago, likely triggered as retreating glaciers destabilized the ground after the last ice age, and it stands as proof that these events can reshape entire landscapes without any magma ever reaching the surface. Researchers have identified evidence for more than 20 major hydrothermal explosions across the park since that period, alongside countless smaller ones that occur somewhere in Yellowstone almost every year, usually far from public attention because they are small, localized, and rarely photographed. Despite everything that unfolded in June 2026, Yellowstone's official volcano alert level has remained at normal, and the aviation color code has stayed green throughout. Earthquake activity has stayed within its typical background range. Ground deformation has followed the same slow rhythm of rising and settling the park has displayed for decades. There has been no sign of gas emissions consistent with magma pushing upward, and everything observed fits comfortably within the kind of behavior scientists expect from an actively evolving geothermal system, not the buildup to anything larger. In other words, the giant beneath the park has not been waking up. A relatively small, well-documented patch of ground rearranged itself in a way scientists have simply never been able to observe this closely before. That is really the heart of this story, and it is far more interesting than any headline claiming the supervolcano is stirring. For decades, researchers have wondered whether hydrothermal explosions give off any detectable warning signs before they strike: subtle earthquake patterns, shifts in underground pressure, faint acoustic signals, anything that might allow a hazardous area to be closed before disaster instead of after. Until June 2026, nobody had the right instruments sitting close enough, at the right moment, to answer that question with confidence. Now scientists have weeks of extraordinarily detailed data to comb through, hunting for any signal buried in the noise that preceded the explosion. If they find one, it could change how hazardous geothermal regions are monitored not just in Yellowstone but in places like Iceland, Japan, and New Zealand, anywhere large numbers of people walk daily across ground with boiling water hidden just beneath their feet. If they find nothing at all, that answer matters too, because it would confirm that some of these events simply cannot be predicted with today's technology, which is valuable information in its own right for anyone managing safety around thermal areas. Temporary seismic stations have since been added directly around the new vents, giving the observatory an even denser web of instruments than the one that already captured the June event, and teams have been returning to the site on a regular schedule to track how quickly the fresh pool is changing shape, temperature, and behavior. That kind of follow-up monitoring rarely makes headlines, but it is exactly the slow, methodical work that eventually turns a single dramatic event into real, usable science. Meanwhile, Biscuit Basin remains closed while researchers continue watching the new vents, the fresh boiling pool, and the surrounding ground for any further movement. That is really what Yellowstone has always been, a landscape in constant negotiation with the heat trapped beneath it, opening new pathways in one place while sealing old ones somewhere else, turning a quiet patch of forest into a steaming feature almost overnight and occasionally reversing the process just as quickly. The volcano that produced those catastrophic eruptions hundreds of thousands of years ago has not vanished, and someday, on a timescale measured in tens or hundreds of thousands of years rather than anything relevant to any of us personally, it will erupt again in some form. But the vast monitoring network watching over the park today, hundreds of seismometers, GPS stations, satellite instruments, and now an unprecedented dataset from the closest hydrothermal explosion ever recorded, exists precisely so that scientists are not caught by surprise if the far more dangerous kind of unrest ever does begin. For now, what happened beneath Yellowstone in the summer of 2026 was not the beginning of a countdown to catastrophe. It was a rare, close-up look at the ordinary, restless, ever-shifting nature of one of the most closely watched patches of ground on the entire planet, and quite possibly the key to finally answering a question researchers have been chasing for generations.